Let's look at some examples of finding the area between two curves. So here we see a region which is bounded by the curves y equals x cubed and x equals y squared. X equals y squared is a parabola that's lying on its side and opening to the right, so it's this curve right here. Y equals x cubed is the cubic that you see here, or at least you see part of the cubic. We want to find the area between the two curves, which is this region right here. Our objective is to use an integral to compute this area. Now, in order to do that, it's necessary to determine the equations for the curves, and it's also necessary to determine your starting and end values for your variable. In this case, both of these are functions of x, or at least can be viewed as functions of x. The curve on the bottom is y equals x cubed, which is a function of x. The top curve that you see here is not necessarily a function of x if you look at the whole parabola. The whole parabola does not satisfy, or the graph of the parabola does not satisfy the vertical line test, so it's not a function of x. However, we're only interested in the top half. So if you just look at the top half, that's y equals the square root of x. So that's the top half here, y equals the square root of x. And that's a function of x. So what we can do is we can choose x values, and then for each x value find the cross-sectional length, like so. And if we can determine the length of that cross-section, that will enable us to compute the area by integrating. The area will be the integral of L of x dx. Now we need to find a starting value and an end value for the definite integral. The starting value is the smallest x value, and the end value is the largest x value that exists in this region. Those occur at the points of intersection. Now it's possible you can guess what these points are just by looking at the graph, but let's find the points of intersection exactly, without guessing. Points of intersection. We're looking for the places where the curves have the same x values and the same y values. So if y is equal to x cubed is the same y value as y equals the square root of x, then that means that x cubed is equal to the square root of x. And so if we square both sides, then we'll have x to the 6 equals the square root of x squared, which is just x. So x to the 6 minus x is equal to 0. If you factor out an x, you get that x times x to the 5th minus 1 is equal to 0. So x equals 0, or x to the 5th equals 1. If x to the 5th equals 1, then x is equal to 1. The 5th root of 1 is 1. So x equals 0 is here, and x equals 1 is here. Now if x is equal to 1, then y is equal to 1 as well, because y is x cubed. And down here they're both 0 at the other coordinate, at the other point of intersection, 0, 0. So now we have our smallest x value, which is 0. So the smallest x value is 0, and the largest x value is 1. So keeping that in mind, we can now set up our integral. So the area is equal to the integral from 0 to 1, L of x dx. Now we have to determine what L of x is. L of x is the length of this cross-section. Since we have the same y values, the distance between the 2 points where this cross-section intersects the curves is just the difference in the x values. So L of x is equal to the largest of the two, which is the top curve, square root of x, minus the bottom, which is x cubed. So the area is equal to the integral from 0 to 1 of the square root of x, which is the top curve, minus x cubed, which is the bottom curve, dx. So once again, the reason why we're looking at the difference between the top curve and the bottom curve is we're measuring the length of this line. The length of this line is the distance between the point where the line intersects the top curve and the point where it intersects the bottom curve. So we want to find the distance between those 2 points. They have the same x value, so we just have to look at the difference between the 2 y values. So the largest y value is the square root of x, which is up here, and then the smallest value is x cubed, which is down here. So that's how we end up with this formula. And now we can simply integrate it. This is equal to the integral from 0 to 1. Well, we've already written that down. Let's just integrate it now. Well, maybe it'll help to write this as x to the 1/2 minus x cubed dx, because now we can see that this is the power rule. So x to the 3/2 divided by 3/2 minus x to the 4 over 4 between 0 and 1. So this is 2/3 x to the 3/2 minus 1/4 x to the 4th between 0 and 1. If you plug in x equals 1, you get 2/3 times 1 minus 1/4 times 1 minus, and if you plug in 0, you just get 0 for both of these. 0 minus 0, of course, just 0. So you end up with 2/3 minus 1/4. And if you give them a common denominator of 12, that's 8 minus 3, so 5/12. So 5/12 is the area of the shaded region. In this example, we used vertical cross-sections, but you could equally use horizontal cross-sections. So let's revisit this problem and do it using horizontal cross-sections. So let me just scroll up. Conveniently, we have the graph here yet again. This is the same picture as before. So we have x equals y squared is the parabola opening to the right, and y equals x cubed is the cubic that you see here. We've already established that they intersect at 0, 0 and 1, 1. These are both functions of y. X can be viewed as a function of y, because if you draw a horizontal line, you can see that it intersects each curve only once, at least in this region. So, and beyond, in fact, because here we have y is equal to x cubed, but you can rewrite that as x equals the cube root of y. So you can see that we have x as a function of y. So this one can be our function f of y, which is y to the 1/3. Here we already have this written as a function of y. We don't need to change anything. So this is g of y equals y squared. It's important when you're doing these problems to understand which is the smallest function and which is the largest function. Since we're looking at horizontal cross-sections, we're going to pick a y and we're going to slice through horizontally, like so. What we need to do is determine the length of this line segment. This line segment, the length of that line segment, of course, depends on y. So if we want to determine the length, we have to find the distance between the points of intersection between that line segment and the curve, or the curves plural. So we need to find the distance between this point and this point. They both have the same y value, whatever this y happens to be. So in order to determine the length, ly, we simply need to find the distance between the x values. The largest x value is here. The larger the x value, the further it is to the right. And here we're looking at y cubed. Or not y cubed, we're looking at y equals x cubed. So that's when x is equal to the cube root of y. So the function f of y equals y to the 1/3, that's further to the right, at least in the region that we're interested in. Remember, we're only interested in this region. The two graphs exchange roles wherever they intersect, but we're not interested in what's happening beyond the points of intersection. We're just interested in this shaded region. So the rightmost curve here is the cubic, y equals x cubed, which we're rewriting here as x equals y to the 1/3. This is our f. F of y is y to the 1/3. So the largest value of x is when x is equal to y to the 1/3. So it's y to the 1/3 minus the smallest value of x, which is right here. Now on this part of the region, the graph is x equals y squared. So for this given y, we know what x is. It's y squared. So it's going to be the distance between these two, y to the 1/3 minus y squared. And that gives me the length, L of y. You can see it's the distance between the two x values. The larger x value is y to the 1/3, and the smaller x value is y squared. Keep in mind that y is constant here. We've picked a y, so y is not changing. The only thing that's changing is x. That's why we have a horizontal line segment. The largest x-coordinate is where x is equal to y to the 1/3, as you can see here. The smallest x value is where x is equal to y squared. So if you want to find the distance between them, you just subtract them, like so. So the area is going to be equal to the integral, and again we're going to be integrating now with respect to y, so it's L of y dy. And the bottom limit of integration is the smallest y value, and the upper limit of integration is the largest y value. Again, we can see those from the picture because the smallest y value is when you're at the origin, when y is equal to 0. So the smallest y value is y equals 0. And the largest y value is when you're up at this point of intersection up here, where y is equal to 1. So that's y is equal to 1. So the area is equal to the integral from 0 to 1, L of y dy, which is the integral from 0 to 1, L of y is y to the 1/3 minus y squared dy. And now we have similar computations to what we had before. These are power rule. You add 1 to the exponent, so we're going to add 3/3. 1 plus 1/3 is 4/3 over 4/3 minus y cubed over 3 between 0 and 1. So this is 3/4 y to the 4/3 minus 1/3 y to the 3rd between 0 and 1. So if you plug in 1, you're going to have 3/4 minus 1/3 minus, and if you plug in 0, you get 0 minus 0, which is 0 just like it was before. So now you have 3/4 minus 1/3, and you want to give them a common denominator of 12. So you're going to have 9 minus 4 is 5/12. And that should be what we had before. Let's just scroll up, 5/12. Yes, indeed, it's the same. It doesn't matter what method you use. An area is going to be the same no matter how you compute it, so you'd better get the same answer. Let's do another example. We want to find the area between these curves. The area of the region bounded by the curves x equals y squared minus 1 and x minus y equals 1. The first of these two curves, x equals y squared minus 1, this is a parabola lying on its side, opening to the right. So you can see that that's this region right here. Or that's this curve, rather. That's y equals, or x equals y squared minus 1. The other one we have here, x minus y equals 1, that's a straight line. So that's this straight line, x minus y equals 1. Computing the area here will involve computing the cross-sectional length and then integrating it. Now you can either use horizontal or vertical cross-sections. For this particular problem, it makes sense to use horizontal cross-sections because if you use vertical cross-sections, you can see that your upper and lower function changes at some point. Well, the upper function is the same, but the lower function changes here. Here it's a parabola, and here it's the line. So it makes sense to use horizontal cross-sections because we have a function of y. Notice that here that we have the x as a function of y. So this can be our function g of y equals y squared minus 1. I called it g of y because it's the leftmost function. Remember, the leftmost function means the smaller x value, and the rightmost function, which in this case is the line, is the larger x value. We can also rewrite this line as a function of y. X equals 1 plus y. So now 1 plus y, that can be our f. So f of y equals 1 plus y. So that's this one right here. F of y equals 1 plus y. And again, our parabola here is g of y equals y squared minus 1. So what we want to do is we want to compute the area of the region that they bound, which is this region right here. The region that they bound. Now, in order to do that, we need to know what the cross-sectional length is. We can do that by picking a y and slicing across to get our horizontal cross-section. Then the length we can call L of y. L of y is the larger of the functions, f of y, minus the smaller of the functions, g of y. So remember what this is really doing for you. L of y is really the length of this line segment. So you have to find the distance between these 2 points. They have the same y value, so the distance between the 2 points is just the difference of the x values. Over here on the right, the x value is given by 1 plus y. X is equal to 1 plus y. That's the line. X is equal to 1 plus y. That's this one. X is equal to 1 plus y. So that's this x value right here, 1 plus y. Over here on this side, x is given by the parabola. So x is equal to y squared minus 1. So this x value right here is y squared minus 1. So those are the 2 x values. So in order to find the length, you take the largest x value, which is 1 plus y, and from that you subtract the smallest x value, y squared minus 1. That's L of y. We can simplify that in a moment. First of all, the area is going to be the definite integral of this quantity, L of y, with respect to y. But we need to know what the smallest y value is. That will be our lower limit of integration. And then you also need to know what the largest y value is. The largest y value is going to give you your upper limit of integration. So we need to just determine what those values are. And how do we do that? Well, the smallest y value in the region is right here, where the line intersects the curve. The largest y value is up here. That's the highest point. So the smallest y value is the lowest point in the region, and the largest y value is the highest point in the region. You can see that these are the points of intersection. So we need to find the points of intersection. And in order to do that, we're trying to find where these 2 equations have the same x value and the same y value. So in particular, since we're viewing these as functions of y, we have f of y is equal to 1 plus y, and g of y is equal to y squared minus 1. We want to find the place where they have the same x value and same y value, but these are the x values. So if the 2 x values are the same, then 1 plus y must be the same as y squared minus 1. So now we have a quadratic expression for y. Y squared, subtract this y over to the other side, minus y, and then subtract this 1 over to the other side. So minus 1 here, you're going to have minus 2 equals 0. This is a quadratic. So you can factor this quadratic. y 2, 1 minus plus. So that tells me that y is equal to 2 and y is equal to negative 1. So you can probably see that it's 2 on the graph, but just because it looks like it's 2 doesn't mean it actually is 2. That's why you really need to check these things. And you can just also check that the x value here is 3. So it's 3 comma 2 is that point. Let's write it above so it's not quite as cluttered. 3 comma 2. That's that point right there. If you're not sure how to get that, just take the y equals 2 and plug it back into here. If y is equal to 2, then x is 1 plus 2, which is 3. So that's how I know that it's 3. What about down here? Well, you can probably guess that x is 0 there, but y is certainly minus 1. We've just found that. So we have that x is equal to, and again, you can just plug it into here, x is equal to 1 plus a negative 1, which is 0. So this point right here has x-coordinate 0 and y-coordinate minus 1. But what we need is we need the y-coordinates. So the smallest y is y equals minus 1, and the largest y is y equals 2. So this is y equals 2. So the area is the integral from minus 1 to 2 of L of y, which is 1 plus y minus y squared minus 1 dy. And now let's just simplify that. Minus 1 to 2. 1 minus a negative 1 is 2, plus y minus y squared dy. All of these can be computed using the power rule. So this is 2y minus y squared over 2 minus y cubed over 3 between minus 1 and 2. So at the upper limit, you have 2 times 2 is 4 minus 2 squared is 4 over 2, which of course is 2, minus 2 cubed is 8 over 3, minus, and now we plug in the lower limit, which is a negative 1. So we have minus 2 minus 1 half, negative 1 squared is a positive 1, and then minus a negative 1 over 3. So if you do all of the arithmetic, this should end up as 9 over 2. And that's the area of the region. It is possible to compute the area of this region using not horizontal but vertical cross-sections. So this is the same region, just reproduced. Now, let us remind ourselves what these two curves are. The parabola has equation x equals y squared minus 1. So that means that this vertex right here, the vertex of this parabola, is at x equals minus 1 because y is equal to 0 there. That's the parabola. What about the line? Well, the line, you may recall, had equation x minus y is equal to 1. Just to remind ourselves that that's what the equation was. X minus y is equal to 1. Okay, so it is possible to view these as functions of x. Well, it isn't possible to view the parabola as a function of x, but you can view it as two functions of x. Because if x is equal to y squared minus 1, you can solve for x. So you'll have y squared is equal to x plus 1. So y is equal to plus or minus the square root of x plus 1. Now the positive square root, that's the top half. Y equals plus square root of x plus 1, the positive. The negative root is the bottom half. Y equals negative square root of x plus 1. So it is possible to view all of these boundary curves as functions of x. So the line here, we can just solve that one for x, and that's going to give us that y is equal to x minus 1. If you just add the y to both sides and then subtract the 1, that's what you'll have. So you can view all of these regions as functions of x in that way. So what does that do for us? That means we can compute the area of this region by looking at vertical cross-sections. But you have to be a little bit careful, because if we do a vertical cross-section on the left half, perhaps half isn't the right word, but on the left side, the left of the y-axis, the upper bound, the upper curve, is y equals the square root of x plus 1. And the bottom is still the parabola. So the bottom is y equals minus the square root of x plus 1. So that's fine, except if you look at the right side of the y-axis, you get something different. Let me color these in. So to the left of the y-axis, I'm going to color that blue. So that way I can just call it the blue part. And to the right, I'm going to color it in as green, so I can call it the green part. So in the left part, in the blue part, you can see that the top half, the top curve is a parabola, and the bottom half is also part of the parabola. But if we move to the green part, it's changed. The top part is still the parabola, but the bottom half is now the line. The bottom curve is the line. So if I want to determine the length L for each x, it's going to depend on whether I'm in the blue region or the green region. So you have to do this separately. So the area here is equal to the integral of L of x, but we're going to have to view it as two separate regions. So first we're going to do the blue. So let me write it like this way. It's the area of the blue region plus the area of the green region. So let's do the blue first. So to do the blue region, you need to set up an integral. It's going to be the integral of L of x dx. Well, what's the smallest x value here? The smallest x value is the point, comes from the point which is furthest to the left, which is where x is equal to -1. The largest x value in the blue region is x equals 0. So you're integrating from -1 to 0. Now what is L of x going to be in this case? So it's the integral from -1 to 0. We're looking at vertical cross sections, so we do the upper curve minus the lower curve. The upper curve is the top of the parabola, which is y equals the square root of x plus 1, minus the lower curve. But the lower curve is also part of the parabola, but here y is equal to the opposite of the square root of x plus 1 dx. So this is the integral from -1 to 0. Minus a minus is a plus. And these two quantities are the same. So this is just 2 times the square root of x plus 1 dx, which is the integral from -1 to 0 of 2 times x plus 1 to the 1/2 dx. So this is something you can do using a substitution. You can let u be equal to x plus 1, and then du is just dx. So this is going to end up being 2, that 2 right there, times u, increase the exponent by 1, so it's going to be 3/2, divided by the new exponent, 3/2, between -1 and 0. So this is 4/3 times x plus 1 to the 3/2 between -1 and 0. 4/3 times, well, if we plug in x equals 0, we're going to have 0 plus 1 to the 3/2 minus 4/3 minus 1 plus 1, that's supposed to be a plus. I was thinking ahead, 3/2, because -1 plus 1, of course, is 0. And 0 plus 1 is 1. So what do we end up with? We end up with 4/3 minus 0 is 4/3. That's just the area of the blue region. Now we also have to find the area of the green region, but we do it basically the same way. we just have a different function now as our lower curve, coming from our lower curve. So it's the integral, well, let's see. What is the smallest value here? Well, the smallest x value, again, is x equals 0. So we have 0 here. And what is the largest x value? The largest x value comes from as far to the right as you can be, which, remember, was this point of intersection. If we just scroll up, you can see the point of intersection was 3, 2, we discovered. So this point right here has coordinates 3, 2. So that means the largest that x can be is 3. And now we're going to integrate L of x dx, but in this case, it's a different formula for L of x. Again, though, we want to do the upper curve minus the lower curve. The upper curve is still the same, so it's the square root of x plus 1, minus, but now the thing that we're subtracting, the lower curve, is x minus 1. So we're going to just subtract x minus 1 dx. So this is the integral from 0 to 3, x plus 1 to the 1/2 minus x minus a minus 1 is plus 1 dx. This one we do using a substitution just like before. So this will be x plus 1, increase the exponent by 1 to 3/2, divide by the new exponent, 3/2, minus x squared over 2 plus x, between 0 and 3. So this is 2/3, x plus 1 to the 3/2, minus x squared over 2 plus x. That's a squared, between 0 and 3. All right, so this is 2/3, so let's do this at x equals 3 first. So 3 plus 1 is 4 to the 3/2, minus 3 squared is 9/2 plus 3. That's at 3. Minus, and now we plug in x equals 0. Now very often when you plug in x equals 0, everything goes away. Certainly those two terms do. But this term does not, because when x is equal to 0, you have 2/3 times 0 plus 1, which is 1 to the 3/2. Then it's minus 0 squared over 2 plus 0. And of course, these last two terms are nothing but 0. But this term is 2/3. What about this term right here? Well, the square root of 4 is 2. And then if you cube that, you get 8. So you end up with 2/3 times 8 minus 9/2 plus 3 minus 2/3. So if you work through all of the details, this should give you 19 over 6. So that's the green, that's the area of the green portion. So that's this bit here. So that's the green portion here. And we also have a blue portion, which was 4/3. So the total area is equal to the blue plus the green, which is equal to 4/3 plus 19 over 6. So to add these together, you give them a common denominator of 6. And so you multiply this one by 2 over 2. So you get 8 plus 19 is 27 over 6. And sure enough, if you reduce that, you get 9 over 2, 9/2, which is exactly what we saw before, 9/2. Again, it doesn't matter which method you use. If you're computing an area, you'd better get the same thing either way.